welcome everyone to the Scripps Technical Forum with Exail. I will go over a few housekeeping items and then turn it over to our speakers. So the Scripps Technical Forum is an opportunity for industry partners and other technical experts to connect with the Scripps community and share technical expertise and new robotics, new softwares, new innovations with the Scripps community, and have an open space for our Scripps researchers to ask questions and really get into the nitty-gritty of these different technologies. So we will be using the Q&A function of the webinar. Please feel free to put your questions in there. Some of you had questions during the registration, so our speakers will also speak to those questions during their presentation. We've got everyone automatically muted. When we get to the Q&A portion at the end, you can put your questions in the chat, or depending on how many of us there are, we can have you come on camera and chat and speak directly with Cheyenne and Olivier. All right, and real quick, we've got a few more technical forums later in fall. 2 in person, RBR and Seabird Scientific will be coming to Scripps campus, and C-Signum will be hosting a virtual webinar in October. Those are all on the Scripps calendar, and you can reach out to us with any other ideas. We'd love to highlight your labs, any collaborations you have, and get more on the calendar. So I will turn it over to Cheyenne and Olivier. We are really delighted to have them here. They're part of Exail, which is an innovative technology company that is from the deep sea to outer space with robotics and new technologies in these really hostile environments. They will tell you more all about them, and I'll hand it over to you. Thank you so much for joining us.
Thank you, Kenan. This is Cheyenne Huck. I'm the Business Development Manager for Exail in the US, focused on offshore maritime, geosciences, and renewables. And my colleague, Olivier. Olivier.
Hello, everyone. My name is Olivier Moisan. I'm based in the Exail in the south of France, and I'm the operations manager for DriX operations, so the operation that are related to the uncrewed surface vessels that Exail is building.
So for this presentation, we'll go through just a very quick overview of who we are and what we do, and about our presence in the US. Some of you may already know us with our previous name. If you're not familiar with the Exail name, until very recently, the name was XBlue. And if you know us for a really long time, you might even know us as Exail. So the Exail is a recent rebranding due to merger of 2 companies in France, Eka Robotics and XBlue. So that's why the new name Exail. I'll quickly go through just a very quick overview of the corporate side of our full capabilities in terms of products and solutions that we offer. We're already quite involved with Scripps in quite a lot of areas technically. And Olivier will go over 2 case studies, one about an annual fisheries and biomass research survey that is conducted with our DriX uncrewed surface vehicle in Northeast wind farms, and also about a multi-vehicle expedition that is conducted by NOAA OECI, Ocean Exploration Cooperative Institute, off the coast of Hawaii. It started in 2022, and it's an ongoing mission that is building on past experiences. So Olivier will cover those 2 topics. Can everybody see the screen?
It looks like we can't.
Okay. How about now?
Perfect.
Okay. So Exail, due to the merger, we're about a 2,000 person company based mainly in France, headquartered in France, just out of Paris. Our focus and our expertise is truly in maritime robotics, underwater vehicles, surface drones, ground vehicles, also in aerospace and defense, navigation and positioning, subsea navigation, such as submarines, AUVs, ROVs, also surface navigations for ships, cargo ships, etc., and photonics, laser capability, quantum, gravimeters, etc. We're located around in 80 countries, mostly in Asia Pacific, Europe, and in the Americas, with a small presence in South America. One of the best things, my background educationally is in electrical engineering. So one of the best things that I like about Exail is the fact that we're always innovating and always contributing towards R&D, and a big portion of our turnover is towards internal R&D because we're always trying to kind of stay ahead in terms of technology and cutting edge solutions. And we have over active patents, 300 active patents throughout. We have 21 industrial sites, again, mostly in France, focused on shipbuilding, inertial navigation systems, acoustic positioning, sonar, seabed imaging and characterization, as well as in aerospace and defense and photonics. In the US, we're about a team of 30 people and located in 2 distinct locations. One team that's based out of Lincoln, Rhode Island, is focused on all the defense applications, so ONR, US Navy, US Army, etc., and mostly DoD activities. And the second team is based out of Denver, Colorado. That is everything that's non-defense, such as offshore oil and gas, offshore renewables, mining, autonomy in terms of autonomous cars, space applications. That's one of our newest activities, a newest market that we're involved in with low Earth orbit space satellites with our gyro compass solutions. As some of you may know, we have a industrial partnership with the University of New Hampshire's Joint Hydrographic Commission, CECOM, and we have recently opened a maritime autonomy innovation hub. The idea being for supporting our clients who are using our uncrewed vehicles, which is the DriX that you see in the middle picture. It's a 8-meter long vehicle, which I'll talk about in a little bit. And of course, to build on that, right now the capability is to train operators on how to use this type of platform, and also be used as a center for maintenance and operation and repair activities. Over time, the plan is to develop a remote operation center for all kinds of over-the-horizon operations for remote hydrography and remote operations. And then also to have a local presence to support all of our clients. That's the eventual goal as we're scaling up, and eventually to have manufacturing capability in the US. And that's one part of it, but because of our industrial partnership with academia, which is something that as a company that's in our DNA, is to constantly find collaboration with academia and with oceanographic institutes. That's kind of the reason why we're here today, is to also foster maritime autonomy education. So for example, we're involved with academia for students to do internships and projects with our team in France, and also for our experts from France to come and contribute towards maritime autonomy activities in terms of workshop, lecture series, etc. So as I mentioned, as a company, we are very much focused on what we call a vertical integration of our vertical chain of production. What we mean by that is we develop a lot of the components ourselves. For example, we have capability to manufacture and extrude our own fiber optic cables. We also develop ourselves all the optoelectronic components that eventually go to all the equipments and sensors that we develop. For example, inertial navigation systems, subsea positioning and acoustic solutions such as USBL, LBL, also in quantum instruments, onboard electronics and simulators for aerospace and defense. So we develop the components, we develop the equipment based on those components, and then a lot of the equipment, for example, sensors and payload, go into a lot of the platforms that we develop. So in this course of this presentation, you'll get a sense for how some of these equipment gets integrated into our platforms, such as USVs, AUVs, UGVs, and then together, what we try to offer is a complete solution to our clients that takes many different aspects and many different components together, either for seabed mapping, for hydrographic survey, for offshore construction operations, etc. And of course, in terms of some of our main applications and markets, these are the areas that we are generally involved with. As I mentioned, in the maritime domain, that's kind of what's relevant for our discussion today. We're involved in a lot of energy and renewables, oil and gas and offshore renewables, as they're kind of getting more and more upscaled in the US. We have been involved in the renewable space quite a bit already in Europe because of our presence there. And of course, hydrography and oceanography, geoscientific, and fisheries. That's kind of what we will focus on today. So just to kind of, before I hand over to Olivier to kind of talk about the case study, I wanted to at least just give a quick overview of DriX, what it is and what it looks like. So it's an 8-meter vehicle that you see in this picture. It's a 8 meters long with a inverted monohull design. It's built completely out of composite with a Kevlar reinforcement. So it's a very quiet data gathering, very stable environment. What you can see in this picture is underneath there's a retractable gondola. That's where most of the payload goes into. For example, multibeam, sub-bottom profilers, USBLs, etc. Anything that you can think of for subsea mapping, tracking, imaging, etc. All the work that we do, and of course, thanks to the availability and accessibility to Starlink, a lot of what we do is what we call supervised autonomy. So it's remote operations, but there's always a human in the loop. At the end of the day, the human command and controls and is the final decision maker on everything. But because this allows us to kind of extend the boundary of where we operate and how we operate. For example, we have a remote operation center in our in south of France at our shipyard in La Ciotat, but we can operate the DriX in Alaska for a fisheries application. We have done that. So we can have a local presence, but then in order for us to have 24-hour operations, it gives us the flexibility and extend the envelope of operation by having this remote capability. And then one of the key aspects of a vehicle like that at the end of the day, and the way NOAA is using it. So right now, NOAA owns 3 of these vehicles, and it's part of their operational fleet. And it's mainly used as a force multiplier. And this is the way they're kind of solving the problem of hydrography as part of their operation. And this is just to free up ship time for other critical missions. And the case study that we'll talk about later on will kind of focus on that and how by freeing up ship time, it allows the ship to do other missions that's more critical, and for the DriX to act as a force multiplier. Just a quick overview. Now we have a complete family of DriX. So we originally started with the 8-meter DriX. You may have seen it. Now we have a 9-meter long, the difference being that it has extended fuel capacity for more endurance. The standard DriX mission, the speed is up to 13 knots with about 4 to 5 days at operations at sea for refueling. Of course, depending on sea conditions and operating conditions. The DriX H9, which is the next one, allows also 13 knots max speed, but almost double the endurance of 8 to 10 knots before refueling. And then our latest DriX, which is 16 meters long, that is complete transatlantic capability with 30 days of endurance at sea. And of course, full ocean going sensor payload capacity, etc. in the middle image, you kind of see the aerial view of the two platforms, the DriX H8 and the DriX O16. And in the O16, as you can see from the top view, there's a back deck that allows for launch and recovery of AUVs, ROVs, other platforms that you can think of. So in terms of applications, there's many different types of applications in the civilian space, also in the defense applications. We do a lot of work in the US Navy with the US Navy for maritime domain awareness, as well as other Navy-specific missions. Olivier, want to hand it over to you for the first case study?
Yes, thank you, Shane. So yeah, hello again, everyone. The idea was to obviously illustrate the capabilities of our USV. So the H8, the smaller version of the USV that we are building, through two different case studies. One that we performed as Exail for NOAA. This is the first one, and another one which is through the acquisition of a DriX from OSCI. So the first one is actually a biomass study on wind farm sites. So that 3 different wind farm sites. If you can carry on, Cheyenne. So the context of this project is that there is obviously a huge development in Europe and in the US of wind farm, offshore wind farm sites. And still very little that is known about the impact of these structures on biomass. What is the effect on population of fish? And so Exail was contracted last year to perform a study of 3 different sites that you can see on the bottom right corner that I highlight. One is Block Island, so that's already a constructed site with 6 wind farms. South Fork 1, and then Vineyard Wind, which are currently under construction. Okay. So why DriX for this operation? Well, for a lot of different reasons. Obviously, the ability to integrate quite a lot of equipment. I mentioned the SeapiX quickly. So the SeapiX is a 3D sonar that allows us to actually analyze a volume of water, and that will allow us to characterize in terms of biomass quantity a large volume of water. So that's the one that you can see on the left. All the equipment is integrated within what Cheyenne mentioned as the gondola. So that's the black structure that you can see. It's actually providing the stability, obviously, of the DriX, because it's has quite a lot of weight. So like for a sailing vessel, it actually allows DriX to stay still even in rough conditions. But we also take the opportunity of this structure to add as many equipment as we can. And so for this particular operation, it was a combination of Kongsberg AK-80s, an ADCP, and the SeapiX all together. We also need a platform with endurance and high speed capabilities. The idea was to try to cover as much areas as possible for a limited amount of time. And I'll go a little bit later on how the operation went and the amount of days that we did the survey. But we could actually survey at 8 to 9 knots, and DriX is able to go to up to 14 knots. So we're not restricted in terms of speed, but we still maintain an endurance. So DriX is able to stay up to 7 days at sea to do the survey, working 24 hours. So it allows to cover quite a lot of area before actually having to come back to port. Did not mention that. So DriX was deployed from port and was going back to port. It's also a platform that is offering a robust and evolved situational awareness and obstacle avoidance system. Obviously, you want to do an operation on whether a wind farm site that is already built, so you've got wind turbines basically everywhere, and on the other side, the other site that you need to investigate is actually half of the site is built and the other one is being built. So you've got construction vessels going in and out. You've got fishing vessels that are still allowed to do to put their fishing gear in the water and to sail. So there's a lot of activities on site, and you're basically supervising the operation for quite far away. And DriX actually allows a full environment of sensors that would detect from a vessel that is going at 25 knots towards your direction that you can pick up at 10 to 15 kilometers away. And at the same time, you'll be able to spot a relatively small fishing buoy. And DriX is able to avoid all of these targets. So once again, it allows you to actually work safely in a complex environment. And the environment is complex as well because we're doing the survey between October and November. So you obviously have to expect from relatively bad weather, and that's what we had. So I think the average wind speed was around 25 knots when we did the operation, and the waves were about 1.5 to 2 meters in terms of average, up to 3 meters during the survey. How did the operation go? Well, as Cheyenne mentioned, we've got an innovation hub at the University of New Hampshire. That's where we actually mobilize whether our DriX or sometimes the DriX from our clients in the US. So that's really our operation center in the US. So DriX number 18 was mobilized for this operation and was actually brought down to Rhode Island on a trailer, like you can see in the picture. And then we basically built a remote operation center at the University of Rhode Island to allow our operators, so our DriX engineers and our scientists, together with the NOAA team, to be able to conduct and supervise the operation remotely. So everything was done fully remotely. We used a high bandwidth satellite connection, so Starlink, and so we were able to obviously see through the cameras, as you can see on the screen here. Actually, we've got cameras all around the masts and even looking down in the gondola, so underwater. And then we've got a full supervision of everything that is happening. And you can see here on the screen, you've got the navigational map where we can see how DriX is actually circling around and getting closer and closer to the turbine. That was one of the patterns that we had to perform to try to estimate the biomass that were close to the wind turbines. So in total, it's 22 days of data acquisition with a total of a bit more than 3,500 kilometers of survey lines, which so in total, it's about 5,000 kilometers of navigation. Basically, we were coming from Narragansett up to the sites and getting out and in every 5 to 6 days, and then doing all of the acquisition 24/7. Mean speed of 7 knots. That was an average speed that was actually providing the accuracy that we required for the data, for the acoustic data, and at the same time, relatively high speed to obviously try to cover as much area as possible. Once again, the challenge was to get close to the turbine, even though the USVs being operated from quite far away. Once again, this is possible through the situational awareness of the drone, but we were getting up to around 20 meters from each of the turbines. And in total, it's about 30 terabytes of acoustic data from the ADCP to the SeapiX to the AKAT's data. So this is an example of the areas that we covered. So basically, what you can see is the track lines. So that's the GPS track lines of all of the sites that we've covered. So you've got different patterns, really long lines that will allow us to actually cover large areas, to have an average repartition of the biomass, and at the same time, you can see those circles around the turbines that are installed that will allow us to get a closer view of and a more accurate view of this biomass that is gathering around the turbines. And then, so that was for Block Island. This is for South Fork, so more or less the same pattern. Long lines going from the west to the east of the area, and then closer lines to get a more accurate and a more focused data set. And the last one is the Vineyard Wind 1. Same, so I would say around 70% of the turbine were installed, and so we focused on some of the turbines, that this concentrated square that you can see on the map, and still again these longer lines to get a wider view of the biomass estimation. So that is an example of what SeapiX is actually seeing live. So you can see on the bottom, it really looks like a swath. For those of you that knows, multi-beam systems to do bathymetry, it's exactly the same principle, but you actually have two antennas in cross, and you can use alternatively one for emission and reception and the other way around. So it really allows you, even if you stay still, to actually insonifiate a 3D mass of water. And that's the type of biomass that we could see on the screens, that we could gather actually. That's one of the pattern that I showed you, circling around and getting closer and closer to the turbine, and that allows us to actually, see this school of fish that is gathering closer to the turbine. So all of the dots that you can see, you cannot see as we are, outside of, out of the turbine. But as we get closer, that is an example of a school of fish that is gathering in the vicinity of the turbine. But also, like I said, SeapiX is a multi-beam. So at the same time that it allows you to actually investigate the water column, you're still able to obviously record the bathymetry. So at the same time, we're able to extract bathymetric data from our scan. So you can see on the right screen, the big red dots is actually the base of the turbine. And you can see all the scours and some of the rocks that can be in the area as well. And other results that we actually did not see, that was not part of the initial scope, is because DriX is obviously recording at all time the cameras, whether it's the infrared camera during overnight, or the RGB cameras that are all around the mast. So that allows us once again to see at 360 degrees. We were actually visualizing marine life, so mainly dolphins, throughout the campaign. And as we were covering quite a large area, it was interesting, and NOAA came back to us because there are hydrophones placed in the vicinity where we were doing our surveys, and so they were able to actually detect through the hydrophones the acoustic noise of the dolphins, and thanks to the images that we recorded, they were able to actually associate the species to the acoustic sounds that they were emitting. So they were able to actually create a map of where the dolphins being picked up and which species it was. So overall, a fully validated concept, DriX performed during this 20 days campaign through weather, through once again a complex environment, and providing really high data quality and operational efficiency. There quite a lot of data was gathered, so there's still quite a lot of processing to do before being able to actually provide conclusions to everything that was recorded. But the mission, the operation was so successful that it's a contract that is now being renewed. So for this year and also for the next 3 or 4 years, it's going to be an annual survey that we are going to do to be able to temporarily match the data of each year's.
This next case study, this presentation is actually always done by Dr. Larry Mayer, who's the director of CCOM at University of New Hampshire. And so Olivier and I will try to do our best to match his ability to present this. But to set the stage for Olivier to kind of get into the technical case study of this, as I mentioned earlier, NOAA has acquired 3 of these DriX platforms in the last 3-4 years. And the very first one that was purchased was through OECI, the Ocean Exploration Cooperative Institute. As some of you may know, that includes University of Rhode Island, University of New Hampshire, University of Southern Mississippi, Ocean Exploration Trust, and Woods Hole Oceanographic Institute. And this mission was first started in 2022, and it's still an ongoing mission as we speak. The 3rd iteration of this mission is happening off the coast of American Samoa. This involved Ocean Exploration Trust's EV Nautilus, working with the DriX as a force multiplier, but also as a command and control for multi-vehicle operation. So when this project first started, the idea was to see how different autonomous vehicles could be used for from a ocean exploration standpoint. So that involved, besides DriX, the deepwater AUV called the NUI from Woods Hole, the midwater column AUV called Mesobot, and Ocean Exploration Trust's ROV Hercules. So there were 2 aspects to this mission when it first started off. The DriX is equipped with the Kongsberg EK80 single beam echosounders, similar to what was presented in the previous case study, as well as a Kongsberg multibeam 2040, as well as a USBL system for tracking underwater vehicles. So that was kind of the payload for the DriX. That is still the payload for the DriX. So the idea was twofold. One, to work as a force multiplier with the EV Nautilus. The idea was that the EV Nautilus, which already has a shipborne multibeam, would collect deepwater data, whereas the DriX would operate as a force multiplier collecting nearshore data. there were times when the EV Nautilus was called for another mission and the DriX was left alone to essentially work as a command and control conduit for these two AUVs, the Mesobot and the Nui. And for this mission, we developed, as you can see from the very bottom picture in the center, that's where you can see the DriX being launched and recovered from a special, what we call a DDS, a DriX deployment system. But for this one, this was a special one made for this project. It's called a universal deployment system because this mission also included an AUV. So it allowed for a launch and recovery of the DriX USV as well as the AUV through a single interface / capability. And so, Olivier, I will let you kind of talk about this project, which was first initiated as a 10-day shakedown cruise off the coast of Hawaii. Then it got progressed to a deep water project, and that's what Olivier will talk about.
Thanks, Jen. Yeah, what's really interesting is that the different step through times and the different type of applications of DriX through this project with OOCI. Like Cheyenne said, it started with a force multiplier idea that we would fit a Kongsberg 2040. I think Cheyenne, you can go to the next one. So that's the initial test. Maybe the next one. Yeah, so that's the initial idea, was to use DriX as a force multiplier. DriX was fitted with a Kongsberg 2040. Nautilus obviously is a bigger vessel, much bigger, and has deeper water multibeam system. So the idea was to have them to work together. DriX focusing on shallower water, multibeam survey. Maybe the next one, Cheyenne, and then the Nautilus obviously working on deeper water. So for example, on this map, you could see a few survey lines that are being filled in the middle. That's the HMI that's the software of DriX. And then the Nautilus is in yellow and green, so deeper sections doing deeper water multibeam. And it's a cool combination because, well, DriX is quite efficient in doing bathymetric survey, and at the same time Nautilus is able to take care of deeper sections. At this time in 2022, obviously Starlink Maritime was not at the level as we have now, and so we were using they were using the Kongsberg MBR, which allows us to work at a distance of around 20 kilometers. So we are not over the horizon. DriX was being piloted from the Nautilus, with DriX being able to go up to 20 kilometers. So it's still a limited range, actually, if you work in wide space like Hawaii. Maybe the next one, Cheyenne. That's still the same principle of DriX covering large area in shallow water, and Nautilus doing multibeam survey in deeper section. But then there is the second concept, which is used with DriX. Like Cheyenne said, there were multiple equipment mounted on the DriX, so a 2040, an AK-80, to be able to actually scan the water column and try to find plankton in the water column, and also a USBL system that was both tracking the robots as they were actually being deployed on the seabed or in the water column. And so we developed at Exail an algorithm that can DriX will automatically follow actually the robot based on the USBL position that is getting from the robot. So as soon as it's getting a position, then it's relocated itself to be always basically on top and circling around the robots. So the idea was to, like they called it, babysit the robots as they were actually investigating the bottom and the water column and interacting with them through the telemetry going through the USBL, so that Nautilus could actually take care of bigger tasks like deep water multibeam, for example, or the tasks. And what they found out was even more interesting than the initial request that was, DriX babysitting the robots. Is like one of the main tasks of Mesobots was to do DNA sampling in the water column in areas where there are plankton. And you can see actually a layer of plankton, which is the blue line. And what you can see in red is actually the Mesobots being detected by DriX that is above on the surface. So it was perfect because you could actually relocate Mesobots to be sure that you place it right in the layer of plankton before actually performing the sample. So it's fantastic because you know that Mesobot is at the right location, and you can just through DriX, once again, you can just send a command to start and do a DNA sample. All of that being remotely operated from the Nautilus. What they could also find is that sometimes when the Mesobot was going inside of this layer, well, the layer was moving. So it's not only about knowing at which depths the plankton is, but it's also the ability to adapt it. So as soon as the Mesobot is getting close to the layer, you can see that actually this blue line is getting up closer to the surface. So once again, you need to relocate the Mesobots to the right layer to be able to basically do your sample in the exact position when you can really gather most of the plankton. And we could really see, they show pictures when you could really see the difference between an empty, what they used to do before when there's a bit of plankton, and really a sample that is full on plankton, when you really know exactly where you need to do your sample. But there was still a limitation. But by the end of 2022, they validated both the force multiplier and at the same time this multi-robot cooperation. That was fantastic. And they did 3 different cruises in Hawaii with the Nautilus. But there was still a missing part, which was the ability of DriX to be able to do deeper multi-beam seabed mapping. And it was quite a big challenge, because basically if you see on the left, that what used to be deeper water multi-beam, obviously it's big, it's lower frequencies, and then the antennas are big, and usually the processing unit is big. So we were really not seeing an option where we could fit something this big into a gondola or into a USV that is just a bit bigger than 7 meters. So we gathered with OCI, with Kongsberg, and they actually built a design for a new multi-beam system, so a new version of their EM712 multi-beam. And we at Exail actually created the gondola that would allow us to actually integrate this multi-beam. So you can see that it doesn't really look like the one that I showed you in the previous case study. It's a bit wide. Obviously, it has a small effect on the hydrodynamic and the consumption, but still we were able to run 12 knots, and we had 1 day less of autonomy. So it was still consistent with with what we wanted to do, actually what it wanted to achieve, which is having 3 to 4 days of autonomy once DriX is being launched from the Nautilus, and so that it could once again do whether the multi-beam survey, but in deeper section, or the multi-robot operation. So in February and March, and also September 2023, there were several campaigns of DriX doing mapping with the 712 and successfully doing mapping with the 712 depths of up to 3,000 meters, which is basically the max specifications of the system. That's the max depths that you can basically reach. And so, because they installed the EM712 and because there was still the possibility to to do this tracking of robot through the USBL, and also because they installed Starlink, there were no longer limitation in the distance between the Nautilus and DriX. So they did some tests where the Nautilus was at 37 kilometers away, which obviously gives you even more flexibility in your concept of operation. And we can see that now with high bandwidth communication system, satellite communication system like Starlink. We are really pushing the limits of what we can do with uncrewed surface vessels in operation. So that was the final achievement, which is actually having the DriX in Hawaii doing survey, but having a team of UNH, of NOAA at the CCOM at the University of New Hampshire, what they called far over the horizon. Obviously, you're a few thousand kilometers away, but you're still able, through the high bandwidth satellite communication, to operate DriX just like if you were actually right next to the USV. So that's fantastic. And like Cheyenne said, they are still actually performing operations. In August, Nautilus was relocated in the American Samoa, where they did a new 30 days operation with a newer concept, which was the DriX going from shore up to a point where it could meet the Nautilus at about 100 miles offshore, and the Nautilus just had launched the robots, and so DriX was just actually meeting the Nautilus, just doing its babysitting stuff, doing some multi-beam, and going back to shore to refueling, where the team was fully supervising him from the shore. So thank you very much. And if anyone has a question, we'll be more than happy to try to answer them.
Great. Thank you so much for that awesome overview. Yeah, so please put your questions in the Q&A or in the chat. Looks like we've got a question in the Q&A. What fuel does DriX use?
It's standard fuel. So it's basically the fuel that you put in any vessel. So it's we've got a thermal engine, but the real benefit of DriX, and I mentioned it in the first case study, is when you see, actually on the picture here gives you a good sense, when you build a vessel with the idea that no one will be on board, well, you build it completely differently than a conventional vessel. So hence the really hydrodynamic shape of the DriX. And that allows us, with having a thermal engine on board, to consume very little fuel. So running 6 to 7 knots survey lines, we consume a little bit less than 2 liters of fuel per hour, around 1.9, which is a huge difference compared to a vessel that would do, 7 days of mission offshore, being able to work when it's 2.5 meter of swell out. So we are at a factor of reducing about 90 to 95% of the fuel consumption, which is and I didn't mention it in the first case study, which was also a big part of using DriX is the carbon footprint. And with a 240 liter capacity on board the DriX, we are running for 4 days.
Great, thank you. We've got another question from Dan about how did you get the permits for the wind farm surveys?
So we engage. I'll start, Cheyenne. I'll let you complete my answer. But we started discussions with both the wind farm constructor and the U.S. Coast Guard quite ahead of the project, introducing our technology, introducing basically all of the documentation in terms of safety that we put in place, obviously, when we prepare a project, and to show that, from our experience, from everything that we put in place, we've got a very safe concept of operation. So the discussion with whether the wind farm constructors or the U.S. Coast Guard actually went really well, and they were really happy to actually allow us to do this operation.
Awesome, thank you. Then we have a question. What challenges do you experience when surveying for these offshore renewables? And do you think those challenges or experiences might differ on the West Coast with the floating wind platforms?
Yeah, there are a lot of different challenges. Some of them are because you're actually performing operation remotely. So sometimes the operator needs to have a sense of what's happening on site with only cameras, and you don't really, because DriX is a stable platform, you don't really see DriX moving even in rough weather. So it's sometimes difficult to actually see what the weather is and feel really what's the weather is when you're doing your operation. You obviously need to take into consideration a lot of parameters about safety, about the turbines, the navigation in the vicinity, and then for your questions regarding floating wind farm, when one of the parameters is obviously you're working on the East Coast in relatively shallow water. Basically, the equipment that we install on DriX are and except from the second case study that I mentioned, deep water multibeam, but we usually work with shallow water system, which works at high frequency. So we are able to, from the surface, to gather really high accuracy and high resolution data. Obviously, if you're working in 200 and 300 meters of water or a bit less, but on floating turbines, there's a question of what is the accuracies that you need to provide if you are doing seabed mapping, for example.
Yes, and to add to that, Olivier, another challenge is, of course, if you're familiar with, Olivier touched about the regulatory side of things. Right now, because of an absence of like a uniform regulatory framework or an understanding of these uncrewed platforms, every Coast Guard region operates differently. So as Olivier mentioned, we had a really good experience with in the East Coast and the Northeast. We had a really good experience with the U.S. Coast Guard in the Gulf of Mexico recently for another project. So the West Coast is different because it's different water depths, different environmental requirements, different traffic, different marine environment. So that's another challenge that we expect. But again, this is where I think like a close collaboration with the Coast Guard from early on, kind of showing them the platform, making them go through the ins and outs of the platform really helps as we gear up for a project like that. And also for a West Coast operation, the larger DriX that I showed earlier, the DriX 016, which is the 16-meter long platform that can take full ocean depth sonar packages like a multibeam, that would be a more appropriate payload for those kind of water depths, which are already 1,000 meters. So, and that's different set of challenges for that and different solutions as well. So hope that answered your question.
Great, thank you. Well, we've got a few more minutes before 1 p.m. Do we have any other questions from our attendees? And if not, if there's anything you would like to add, Exail team, please go ahead, or we can say ta-ta for now. All right, thank you everybody for attending, and thank you Exail for this great information. We will be following up for all registrants with a recording of this webinar and the team's contact information so that we can keep the conversations going and stay on the lookout for more information about Exail and the upcoming technical forums. Thank you all
Thank you
very
very
much.
much.
Thank you.
Thank you.